We have an official Duckietown website, duckietown.nctu.edu.tw. People will sooner or later find us. And more importantly, you can find some other informations. I sent you Google Doc link previously, and you can also find it on our website. How to become a Duckietown robotics in 10 working days. Maybe some of you finished this part already, right? And today we will give our DuckyBots a proper name. The name with a meaning behind it. Okay, so everyone will do it today. And this is the plan for today. Okay, so now we are going to enter the second part. Last part today, we will team up again. We will try to force you guys to form project groups. But we will explain that. Yeah, this is a fun part. I think that you can cheat as much as you can and have a demo. Then what will that be? For example, you can just use a joystick to cheat. So this is like an autonomous robot, but you control it behind the curtain. Or yeah, you can think about the scenario. What would be a good demo that prove your idea? Okay. And we will talk about this later. So I hope you guys will use your talent to influence other people in the future. If you have the repo in your VirtualBox, and you can just CD into this folder and type make. And this is a LaTeX file, graphic. It looks pretty complicated, right? A system diagram. But it will actually, when we look into every single package, you will start to feel that, okay, this is kind of makes sense. Okay, so if you have it, please just follow our steps and then try to see if you can see this diagram, or we will also show you some other folders. This is one of a cool demo that whenever people start to make the robot to move, it's more like, oh, this is my child. Finally, it can move. Okay, people usually feel very exciting to finish this step. And actually, even for this joystick demo, there are a few packages involved. We will explain what's a package and etc. very soon. You can see this is the sensor part. This sensor part reminds you about our second lectures. Last time we talked about self-driving car. Back to 10 years, the MIT team. So we have like a perception, and what else? How many people remember what's the system level diagram for the MIT self-driving car? There is a perception, right? So try to find the obstacles, or try to use the LiDAR to find a drivable ground, right? And what's the next step? Maybe something about the map, right? And also, next step, that would be something about the control. So how are you going to react to an obstacle or a turn, right? So you can see that on this part, we have the sensor component, and there is a node called a Pi camera. So this is actually the only sensor we use for DuckyBot. Okay, so in your code, you will simply open a terminal and do something like a Rust launch or Rust run, and then Pi camera. Okay, so you will have a process running and keep receiving the image frame. Okay, so I think it's about like 30 frames per second. So this is the first part. Over here, we actually see another node. And this node is called a joy node. So actually, this is another input for your DuckyBot. That is the joystick. Okay, so you have a USB dongle on the Raspberry Pi 2, right? And whenever you press the button, and it will send a message in this system. Okay, And you can also see some squares over here. When you open multiple processes, usually the system will need to create a certain type of message so that the processes can communicate with each other. Okay, so in this example, the Pi camera, and this is called image compressed. So this is essentially that's the width and the height of the image. And the best part is that we try to compress using JPEG so that we won't overwhelm the network. We will keep some bandwidth for other things. Okay, and you can also see that there is another message called sensor message, a joy dot message. Okay, so this is more like your joystick, you left button up or A or X or Y, you press some of the buttons. Okay, so this is the sensor part, the inputs, and you can see this yellow part, it's called a joy mapper. So whenever you press those the buttons, and this joy mapper try to convert those buttons into those events, into how to move the wheels. Maybe left one for one round and the other one 2 rounds and turn left, for example. Finally, the yellow part again, and this is called a Dagu card. And this is actually a node that actually execute your commands. Okay, so essentially, again, left or right, and this is actually more like the driver's side. So how are you going to move your vehicle? So I hope that some of us will reach this part, the joystick demo for today. Don't worry, that's pretty doable. Okay, and when you see your robot starting moving, then I believe you will feel very exciting. Okay, at least I'm very excited. And this is another part. Let me just try to get you some concept. So essentially, this part is kind of identical. So we still have the sensor component, and we have the second part is called line detection and projection. Okay, let me just go through some of the basic idea. And again, the circles, the ellipse, they are the node. So essentially, that's one process in your operating system. Okay, and squares, they are the messages. Okay, and the second part, the line detector and projection, that means that when you get the image inputs, and for example, you can see a real Duckietown over here. And for example, my vehicle is right here, and I can see the white line on my right-hand side, and the yellow on my left-hand side. Okay, and then we need to do some like fundamental image processing so that I know, okay, I'm looking for yellow line, or I'm looking for white, or I'm looking for a red one to stop, for example. Okay, so essentially we will have some image processing in this node. You will say, oh, this is something in 2D, right? Because we only have the camera input. We only have the image. How can I know that how far away the obstacle is from me, right? But don't worry, we will do a camera calibration first. So essentially, we will have the image plane over here, and we will try to find homography, that is the transformation from this one to the ground. Okay, so that as long as we have this homography, every single point in your image pixel, you can know like how far away this point is on the ground. Okay, so essentially the assumption is that all the lines, white or yellow lines, they are on the ground. So this is the second part. We do the ground projection to find the correspondence. And then the next part, we will do the lens filter and control. So essentially, we want to keep the vehicle in the center of the lens. First part here, this is called lens filter. Okay, so essentially we will try to transform those line detections into another coordinate. That is like how far away my position from the white or from the yellow. Okay, so that's one of the coordinate, and the other one is the angle. Okay, so it's more like a Hopf transform or something like that. Okay, so don't worry, it's just like we detect a line segment and we try to convert it to, suppose the vehicle is here, so that this is the lateral distance and this is the angle. And we will convert this angle and this distance into another coordinates. So that, yeah, we will get into that later. Finally, we will send the commands to the Dagu card again to actually make the move. All right, and you may be curious that how do I know that even I give this the left or the right the same amount of movement, how do I know that it will move straight? So that's why we want to do a wheel calibration. That is also in one of the steps. Okay, I think this is one of the interesting application here. In the other step, you are going to create your own package. And this package could be something interesting, something out of our imagination. Okay, but the basic idea is that you have the sensor part, like others, okay, and you have the Dagu card for output, and you try to do something about it. 1、2、3木头人，1、2、3机器人。I don't really know how to say that in English, but the basic idea is that this is a Duckiebot, and you can just put some, maybe just a Vola Jones face detector. There is just one line. In Python, like one line function, and whenever the Duckiebot see a face, it will stop. Okay, so you can imagine that suppose that every one of you have this package running, and you have 10 Duckiebots over here, and whenever you turn, and when the Duckiebot see your face, all the Duckiebots start to move. Okay, yeah, so this is one of the steps. You can use your imagination to create your package. Okay, I believe that also this will be also useful in your own project. So I think previously we have the bull fighting. Right, so this package will be red color detector. Not just the color detector, but also need to know where is the detection so that it can try to chase the red. Now we are going to explain what's the implementation in your Duckiebot. Actually, this is like an acronym for robot operating system. The good thing is that it is open source. It's called middleware. Okay, and the history of ROS, I think it was from the DARPA Urban Challenge. So there were a few teams like Stanford team, Carnegie Mellon, MIT, etc. And actually every single team create their own middleware. And later on they all open source those middleware. And of course, there are some pros and cons for those middlewares, but nowadays, ROS become the most commonly used system middleware. We just talk about the conceptual idea about a package, about the node. We also talk about messages, right? So you can imagine that that is one of the process running. That's a node. And try to communicate with other nodes by message. And actually, the package here is essentially is a collection of nodes. The topic is more like a specific type of message. So we actually seen those things already in those rectangles. Essentially, in ROS, we can use either Python or C++, and we typically put those packages in a folder in a specific way. So in every single package, we will have a file called package.xml. and we will have a file called cmakelist.txt. So that will help the whole system to know, okay, there is a package here and what dependencies I should have. Okay, so for example, your package need to process some image so that you may need the dependency from OpenCV, for example. Okay, and let's take a look at some example. You will see those folders. And every single one over here is a Rust package. Okay, or it's a folder to hold multiple Rust packages. Okay, that's the nodes. It can be Python or C++, and each one is actually a process in your real operating system. So essentially, in your computer, you need to run multiple processes at the same time. So if you hit Control-Alt-Delete, and you will see a process manager coming up, and you will see many processes running in your computer. When you start a Rust node, that will become one of the process. For each one, the nodes try to communicate with each other by the Rust message and in a specific topic. The topic is essentially either maybe an image or a joystick message or some other message. And the best part is that you can define your own message depending on your application. Okay, this is one of the example called lamp filter. So we just look at this package, and you can see that there are few Python nodes in it. Okay, so and in each one, so whenever you type like Rust run package name and a node, it will start a package. Okay. But so you can imagine that in the end, you will have multiple terminals and some multiple packages, and they talk to each other. But sometimes it's just too many processes. So later on, we will handle those in a launch file. Okay. But I think it's still good to know how it works without the launch file. Okay, and this is another package called AppRotag. And you can see in this package, in this SRC, so typically that's where your source code is in your package. And those are the C or C++ file source code, or it's a Python. Okay, Rust master. Before we start any node, we will need to start a Rust master first. So in the Rust command, so you can see this is a master over here, and one master can host multiple nodes. Okay, and the master also try to coordinate what message should go, maybe from node 1 to node 2, etc. Okay, and more importantly, the messages could be from different machines. Okay, so for example, you have a laptop, and your laptop and your Duckiebot connect to the same router under the same local network. And for example, you can open a Rust master on your Duckiebot. Okay, and then you can try to set your Rust master on laptop to this master on Duckiebot, so that the two machines can connect to each other. So this is the command called Rust core. We also have some script to set up multiple machines. Right, for example, yeah, just like how we described, and usually we set the Rust master on Duckiebot. All right, and for Rust messages, actually you can define anything, essentially. And you may feel that this looks more like a programming language already, right? So for example, how are you going to define an image? Suppose you are the creator of the Rust message for an image. How are you going to represent an image? Yeah, actually this is a complicated problem, because even for image, it could be a grayscale image. right? A grayscale, you can, for every single pixel, it could be just 1 byte or 8 bits. So that would be from 0 to 255, right? And you have an array of the pixel, right? And if you have RGB image, and how are you going to define each pixel? So actually, you will have like 3 channels, so 3 bytes each pixel, right? Okay, but sometimes if you want to represent maybe the depth image, and the distance, for example, you have a depth image, that means every single pixel is the distance from the camera to something. Okay, in that case, people usually use float 32. Okay, that would be 4 bytes, right? Okay, or some other different formats. How about, for example, a line segment? Suppose in our line detection in 2D, we detect a line segment. How are we going to represent a line segment in ROS message? At this moment, you may be curious that, oh, line segment, that's easy. Maybe I have point 1 and 2, and each point is just X and Y on the image. So that's it, right? But that's not right. We still need to do ground projection. Then what should we do? Okay, maybe it's not that hard either. So for point 1 and 2, we can also give it X, Y, Z on the 3D space, right? So you can see that we have pixels here, and we have maybe rectangle, and we have a segment, okay? And you can actually see what's the actual implementation of a segment. And you can actually see this is a segment list. That means in one observation, you may see multiple segments, right? And you want to send those segments just in one message. So it's more like a collection of the segments. Okay. And also some other interesting thing, maybe street names or the vehicle pause. So that would be more like X, Y, Z, and pitch, roll, and yaw. Pitch is like this, right? And yaw, roll, and yaw. Okay, parameters, and there are lots of them. We talk about maybe in your line detection, you want to detect red color or yellow color, and typically we transform the RGB into another space called HSV. And we set up a range to say, oh, within this range, we call it yellow. Okay, and in this case, we can actually set it in the ROS parameters, or for your camera, you have the focal length fx, fy, and principal points x and y, right? You have those parameters for your camera. Okay. In those cases, we can actually set it in the ROS parameters. Finally, this is one thing you really want to know, because maybe you don't want to open 6 terminals at the same time, and each one you need to type ROS core, ROS run, camera, right? Camera, and then you can have camera input, and next, and line detector, and next, line projection, and next, then filter, and then control, and Dagu card. Yeah, and whenever you restart your Duckiebot, you need to do this over and over again. That's quite tedious. So we actually can use ROS launch, and you can define many of the processes in the same ROS launch, so that you just need to have one terminal, and then ROS launch and package name and the launch file. So you can predefine everything in this launch file. And the even better part is that you can set your parameters in the launch file. So you can See many of the launch file over here. Okay, so there are lots of launch file in Duckietown already. One of this is called a joystick launch. When you are ready, you git clone and you make, you compile all the codes, you are ready to use all those launch files. Okay, so for example, the joystick launch will start the camera, joy mapper, right? And the Dagu card so that you can control it. And this is more like a combination of a joystick and camera so that it can also subscribe the camera and publish it in a way so that you can see it on your laptop.